Okay, good evening, everybody. Professor Ayorinde welcoming you to another review session in organic chemistry. In today's session, we are going to review for exam number 4 that is scheduled for tomorrow, that is Thursday, November 29. And for this review session, we are going to use a previous exam 4 question that is already on your screen. Okay, but before we get the session started, let me go ahead and acknowledge those of you who are already here. I see Agnes Edukere, Alfreda Woods, Amber Emerson, Area Wale, Ayodotun, Brianna Neal, Siobhan Cummings, Ellie Rono, Godson Adejumo, Elisha McKinsey, Jaconda Capers, Kayla Graves, Kiera Bradley, Martha Margaret Cotton, Maya Reed, Ogechi Emegere, Onyolushaya, Pravin Cheka, Rudolph Brown, Shena Aline, Sandra Oyekere, Taylor Wright, and Tiffany Farrell. I also noticed somebody said somebody also joined us. Nia Johnson also with us. So you are all welcome. I notice we do have a lot of people here today. So anyway, let us get this session started because as much as possible, I would like us to finish the set of questions that are posted on your screen at this moment. These are questions from the previous exam 4. Jaconda Capers, can you go ahead and read this question for us?
Using proton NMR data, how would you distinguish between the following pairs of isomers? You must give the proton NMR data for each isomer in order to distinguish them.
Okay, thank you. Very good. Okay, so what they are asking us to do here is to use the proton NMR data to distinguish between this set of isomers, this isomeric molecule. These are constitutional isomers. B is also constitutional isomers, and C also is constitutional. They are both constitutional isomers. I do want to point out to you, though, in C, there is an oxygen missing here. So let me go ahead and write the correct structure here. This is supposed to be this here. Okay, so this here, this is supposed to be this structure. They were missing the oxygen. Okay. So what you find here, this is just another way of testing your knowledge of the nuclear magnetic resonance spectroscopy. In this case, we are looking at the proton NMR. So they want us to distinguish between this compound and this compound using the proton NMR data. Now, if you are given this kind of question, the first question you need to ask yourself is, let us take a look at this molecule here. Can anybody tell me how many different types of hydrogen do you have in this molecule? Can anybody tell me how many different types of hydrogen do you have here? Okay, 3. Okay, that is good. Let us see here. Let me erase this. You said 3. Okay, anybody else? Okay, 3. Okay. Okay, so where are the three? Let us look at it. If we say this is one set of hydrogen here, another set of hydrogen. Okay, about this here, this is another set of hydrogen. Okay, are you still saying 3? Okay, excellent, excellent. Supposed to be 5. This is another set of hydrogen, and this is another set of hydrogen. If you look at this molecule here, this molecule is not symmetric. Okay, so all of these hydrogens are different. So therefore, I would expect to see 6 signals from this molecule. Okay, so now let us take a look at the other molecule here. Let us take a look at this one here. How many sets of hydrogen do you think we have in this molecule here? 4. Okay, let us see. Supposing we say this is one set, that is 2, and then this one here, get rid of this here. This hydrogen here is another set, so that is 3. Now at this point, this set of hydrogen here and this set of hydrogen here will be equivalent. These are both equivalent. Okay, so therefore we are going to have 4 sets of hydrogen. Okay, so I will say this, the first set, and the same thing as this here. So you could see in these 2 molecules here, we could use the proton NMR spectrum to distinguish between them. That is what they wanted to do. Somebody asked a question for me. Why aren't they equivalent to carbon-2? Which one? Which one? Which one are you talking of? Oh, this one here? You mean this hydrogen here?
Yes.
You mean this hydrogen here?
Yes.
Yeah, okay. Sometimes you could, yeah, go ahead. You could pick up the mic sometimes if you want to ask me a question. Yes. Now, this hydrogen here and this hydrogen here, they are not equivalent. Remember what I keep telling you, how do you determine the equivalency of hydrogen? Supposing I replace this hydrogen here with chlorine, okay, I will get one compound. On the other hand, if I replace this hydrogen here with chlorine, I will get a different compound. And as such, this hydrogen here and this hydrogen here, they are not equivalent.
I missed the fourth one. The fourth hydrogens, why are they not equivalent to the second one? If they're both attached to a C.
Which one? This one here?
Yes.
Oh, which one? Which molecule? This molecule
The
here?
fourth, yes. The ones that are labeled as the fourth hydrogen, why are they not equivalent to the second one if they're both attached? They're all attached to a CH.
Okay, now, look at, okay, I have 2 molecules here. I do label this as number 4. Are you referring to this here? Look at this here. Yes, okay. Now, you say, why is this not equivalent to this here? Use the same guideline that I just gave you. If you replace any one of these hydrogen with chlorine, you will get a different compound from if you replace this hydrogen with chlorine. So that is what you have to use as a guideline. To test whether a set of hydrogens are equivalent, just replace any one of them with chlorine and see whether you get a different compound. Okay. So anyway, in this particular instance here, we can use the proton NMR spectrum to distinguish between this molecule here. Let me call this molecule B. Let's call this B, and let us call this A. Okay, we could use proton NMR data to distinguish between molecule A and molecule B, because in molecule A, you will have 5 different signals. On the other hand, in molecule B, you will only have 4 different signals. Okay? Okay, so now let us go to number B. Let us go to B. Let me read this. For B, yes, that's all you have to do. In other words, they are asking us, how would you use the proton NMR spectrum to distinguish between these two molecules? Yes, that is correct. About B, let us look at B. How would you use a proton NMR spectrum or data to distinguish between this and this? Let me label them. Let me say this is molecule C, and let us call this molecule D. Okay? Let me ask you a question here. How many different types of hydrogen do you have in molecule C? 2. Excellent, excellent. Okay, where are these 2? Okay, let us say this is one set. This here and this here will be equivalent because this molecule is symmetrical. And then this set here and this set will be equivalent. So therefore, you are going to have 2 types of hydrogen in this molecule. Then the next question I have for you is this. How many signals, how many chemical shift signals do you expect in this molecule? How many? Exactly, only 2, because you only have 2 types of hydrogen. Okay? You only have 2 types of hydrogen, so you will only get 2 sets of chemical shift signals. Okay. Let us take a look at D. Let us take a look at D. So about D, how many different types of hydrogen do you have here? 4. Okay, let us identify them. This is 1 set. This is 2. This is 3. And this is 4. So therefore, what you have to do here, you have to simply say that in this molecule here, you have only 2 signals in the NMR data or spectrum. On the other hand, in this molecule, you will have 4 signals, 4 different signals. Okay, so that is the one way in which you can use the NMR data to distinguish between this molecule C and molecule D, and that is all you need to do here. So would compound A have 5 signals? Which compound A? Which compound A are we talking of here? Are we going back to this here? Are we saying this here? Okay, this compound A here, how many signals will it have? We say 1, 2, 3, 4, 5. Yes, compound A will have 5 signals. Yes, that is correct. And of course, this here, okay, of course, we have 4 signals. This one here, 1, 2, 3, 4. The same thing for compound C here, we have only 2 signals, okay, for here. Whereas this compound D will have 4 signals, okay? Okay, so now let us go to this here. C. Let me see, any other question here? Okay, I think I answered all the questions. Okay, let me erase this. Okay, let us do C. In this case, let me go ahead and call this compound E. Let me call this compound F. Okay? So just for clarity here. Okay. The question that I want to ask you is, how many different types of hydrogen do we have in compound E? Say 3. Somebody said 3. Let us see. Let us see that. This is 1, this is 2, and this is 3. So therefore, we expect to see 3 signals here. Okay, about compound F. How many signals do you expect? Oh, by the way, I'm sorry. I remember I told you that the oxygen is missing here. Let me go ahead and write that back here. Okay, this is supposed to be this. I think they make a mistake here. The oxygen is missing. Supposed to be this. Okay. Now, let us now take a look at F. How many different types of hydrogen do you have in compound F? 3. Somebody said 3. Okay. This is 1 set, 2 set, and 3. So therefore, we cannot use the fact that we have 3 signals to distinguish between them, right? So this will have 3 signals. Okay, so now what do you think we are going to use? What do we need to use here? This is a little bit more difficult than the previous ones. Since we cannot use the signals, the number of signals, then we have to go deep into the chemical shift exactly for each one of them. Let us now see. Let us now see. We go through the chemical shift, the multiplicity, then we have to give the details of this here. Okay, let us give the NMR data for this. So this here, methyl, we will say that would be about 2.2. That's a methyl next to a carbonyl, and that is a singlet, and that is 3 hydrogen. Okay. Then we look at this here, this CA2 here. What do you think the chemical shift will be? Anybody? You could take a look at your chart. Just give me somewhere within the range. Okay. You should have your chart with you all the time. I would say this might be about 4.0. Okay, 4.0. Okay, and that would be, what would be the multiplicity for this one here? What would be the multiplicity for this here? We can have the chart. Oh yes, you use the chart all the time. You have to use the chart all the time. That is the only way you get to know most of these chemical shifts, unless you've already familiarized yourself with them. So that is a quartet. Okay, and that is 2 hydrogen. Okay, how about this one here? What will be the chemical shift of this? Give me some range. It's not directly attached to oxygen, but it's not too far from it. I would say maybe about 1.2. Okay, what will be the multiplicity? Yes, that is correct. Afraid that was correct. Multiplicity will be a triplet. Very good. Triplet. And 3 hydrogen. Okay, now, let us now take a look at the proton NMR data for this here, compound F. Let us start with this methyl here. Okay, this methyl here. What will be the chemical shift? I would say about 4.2. 4.2. What will be the multiplicity? What will be the multiplicity for this? Exactly, singlet. Okay? And that is 3 hydrogen. Then we take a look at this here, the CH2 here. Okay, this next to carbonyl. Okay, so I will give that about 2.2 or so, somewhere in that range. And what will be the multiplicity of these hydrogens here? Quartet, very good, very good. And that is 2 hydrogen. And finally, how about this one here? Chemical shift will be, I would say, maybe about 1.3. And what will be the multiplicity? triplet. Excellent. And that is 3 hydrogen. So in this particular instance, this here is a little bit more detailed. You need to go into provide the chemical shift information. Provide the PNMR complete PNMR data information for compound E and compound F in order to be able to distinguish, use the PNMR data to distinguish them. Okay, somebody asked a question. Go ahead. So anytime the signals are the same for different compounds, we should use, well, not only do, yes, that is correct, not only do you use multiplicity, you almost have to use the complete set of data. Okay? Yeah, go ahead and ask your question. Somebody asked, so if, yes, go ahead.
Why is the methyl on the side of the ester? Why is that methyl a singlet?
This here? This one here?
Yes, that one. Yes.
Okay, because this methyl here is attached to oxygen and it is not seeing any hydrogen. Keep in mind the n+1 rule. That is 0 plus 1 equals to 1, which is singlet. Okay, because it is not seeing any hydrogen. Okay? Okay. So anyway, in this particular instance here, you look at this data here, you see that the NMR data for this is definitely different from the NMR data for this here. In this instance here, this methyl, which is a singlet, is at 4.2, okay? Whereas the methyl here, which is a singlet, is at 2.2. So you could see the difference in chemical shift. So we could use the chemical shift data here to distinguish between compound E and compound F. Is that clear to all of you? The message here is, if you cannot use the simple case of number of signals, then you have to go into greater details to give the complete set of data for the NMR, the complete set of NMR data in order for you to distinguish between the two molecules. Okay, somebody is asking a question. Where did the numbers 2, 2? Okay, these numbers come from the chart of chemical shift that is in your book. You will find that on page 475 of your book. So you need to familiarize yourself with that chart. And you bring that chart to the exam or to the quiz whenever you're taking an exam or taking a quiz. Okay? Okay, so let us go to the next one. Okay, Brianna, can you go ahead and read this question for us?
Provide possible PNMR data for the following compounds.
Okay, thank you. Very good. Now, notice here, this question here is very similar to the last one, but we are asking you the same concept in a different way. We simply want to see whether you do understand the concept or the theory behind or the principle behind the proton NMR spectroscopy. In this case, they want us to provide the possible NMR data for the following molecules. Okay, let us start with molecule A, cyclobutane. Cyclobutane is this here. Okay, if that is cyclobutane, let me ask you this. How many different types of hydrogen do you have in this molecule? One. Excellent. And I do want to let you know right now, equivalent hydrogen do not split each other. They have the same chemical shift and they do not split each other. So therefore, what will be the chemical the PNMR data for this molecule? What will it look like? We know that it will have only one signal. So what would it look like? Okay, it's hydrogen. What would be the chemical shift? Give me a rough idea. Okay, very good, very good. Somebody said 1.4. Okay, parts per million. What would be the multiplicity? Multiplicity? No, they do not split each other. Okay, equivalent hydrogen do not split each other. Okay, Tiana, you are welcome. Okay, no, they do not split each other. They see nothing. They see zero exactly. To be a singlet. Seeing nothing. So therefore, and that would be 8 hydrogen. So the chemical shift at the NMR data for this molecule, this is what it would look like. In other words, if you have the spectrum, you have TMS here at 0 parts per million, and then you have this 1.4 here, this peak here, which would be a singlet. That would be 1.4, and that is what is the NMR spectrum for this molecule will look like. Okay. Somebody asked a question: why is it a singlet and not a quintet? Because equivalent hydrogens do not split each other. Okay, they do not split each other. Okay, now let us go to B. Bromocyclobutane. Bromocyclobutane, which is this here. Okay. Now let me ask you this. How many different types of hydrogen do you have in this molecule? Bromocyclobutane. How many? You say 2. No, let us look now. Let us see. Somebody said 3. Okay, let us see. Okay. This is 1. Keep in mind there's an hydrogen here. That is 1. This here and this here will be equivalent. So we say that is 2. Okay, and then this is 3 right here. Okay, so you are correct. It will be 3. What page is the information on? What information are you talking of here? The chart is 475. Okay. Okay, so we have 3 types of hydrogen in this molecule. So therefore, how many chemical shift signals do you expect? 3. 3. Okay, now let us give it. Let us give it. Okay, let us start with this. Okay, what do you think the chemical shift of this will be? It is attached to electron withdrawing group. This hydrogen here. Okay, say, okay, you want to give 4.0? Okay, I'll take that. Okay, what will be the multiplicity? Keep in mind now, this hydrogen now is seeing 4 hydrogens. Quintet, very good. Very, very good. Quintet. And how many hydrogen would that be? 1 hydrogen. Okay, so now let us go to the next set of hydrogen. Okay, this hydrogen here, somebody asked a question. Go ahead and ask your question.
So, can you explain how is a quintet?
Okay, because this hydrogen here is seeing these 2 hydrogens here and these 2 hydrogens here. And we have M+1 rule, which is 4 plus 1, which equals to 5. And that is why you have quintet. Okay, because it is seeing 4 hydrogens. Okay, so now we have, let us focus on this here. This hydrogen here, what is this hydrogen seeing? Also the same thing as this hydrogen. What are they seeing? They're seeing this here, this hydrogen here, and they're seeing 2 hydrogens here. So how many total number of hydrogen are they seeing? 1 here and 2 here. How many are they seeing? They're seeing 3. So 3 plus 4 is a quartet exactly. So therefore, I will expect this to be the chemical shift, of course, will be somewhere maybe about maybe 1.5 chemical shift. And then I would say in this case, since this scene, 2 here and 1 here, that's a total of 3. So I would say that's a quartet. If you say quartet, I will let you go on that. But it is a little bit more complex than that. But at your level, quartet is fine. Okay? And then that would be how many hydrogens? How many hydrogens? 4, exactly. 4 hydrogens. Okay? Now let us now come to the set of the hydrogen 3, set 3, this here. These 2 hydrogens here. What are they saying? What are they saying? How many hydrogens are they saying? Okay, seeing, exactly. Seeing 4, exactly. Seeing this here. So therefore, the chemical shift could be about 1.2, and that will also be, what will be the multiplicity? Quintet, exactly. Very good. And how many hydrogen? 2 hydrogen. So, what have we done here? We have also given the PNMR data for this molecule. Okay, and that is what we've done here. Okay, so let us go to the next one. Okay, is it okay for me to erase this so I have some room here? I know some of you are writing down notes. Okay, yes, okay, good. Okay, now let us do this one here. 2-hydroxy, 2-methylpropane. Let us see what that looks like. 2-hydroxy, 2-hydroxy, 2-methylpropane. Propane, that's 3 carbon chain. 2-methyl. Okay, very good. And that is this here. Okay, now let me ask you, you know the question I am going to ask you, how many different types of hydrogen do you have in this molecule? Try some more, try some more, try some more. 2, exactly. 2 different types of hydrogen. And the 2 different types of hydrogen are this one here. And then all of the methyl group, the hydrogen on the methyl group are equivalent. Because this is symmetrical here, they are equivalent. Okay, so I will say 2. 2, that is 2 sets of hydrogen in this molecule. And so therefore, how many chemical shift signals do you expect in this molecule? 2. Very good, very good. Okay, what will it be? Let us give it. What will it be? We have, let's start with this one here. What would this one be? Anybody has an idea? Look in your chart. The methyl. Okay, I would say maybe about 1.6 because it isn't too far from oxygen. 1.6. And what would be the multiplicity? Anybody has an idea what the multiplicity would be? This here, this here. Multiplicity, singlet, because there is no hydrogen on this carbon. Okay, singlet. And how many hydrogen? How many hydrogens? 9. Excellent. So now you have 9 equivalent hydrogen. Okay. Now we have only one set of hydrogen to go. What will be the chemical shift of this hydrogen which is attached to oxygen? According to your chart, the range is kind of broad. So just give me anything within that range. 2.5, okay. That's the low end. Okay, I'll take that, 2.5. Okay, and what will be the multiplicity? Yes, 4 is also correct. Singlet. Okay, very good. Because you do not see any you do not split through oxygen, so therefore this is a singlet and one hydrogen. And so what do we have here? This is the NMR data for this molecule. Okay, go ahead and ask a question. Somebody ask a question. Oh, Praveen said, or somebody said, why 1.6? Okay. 1.6, if you look at your chart, this metal here is attached to this carbon, okay? But this carbon is also attached to oxygen. So you find that this carbon is not directly attached to oxygen. So therefore, I do not expect this to be greater than 1.5, or greater than 2. So it will be somewhere between 1 and 1.8. So take a look at your chart. You will see something in that range. Okay? Okay. Okay, now let us go to D. D, yes. Go ahead and ask your question. Somebody ask a question. Very good. Go ahead. You guys are very active tonight. That is good. Okay, why and it 3? Chart says, which one is, no, because this, okay, why don't you have 3 sets of data? This metal, and this metal are equivalent. If you replace any one of these hydrogen with chlorine, you will get the same compound. Okay? So that is the guideline that I want you guys to use whenever you want to determine whether a molecule, whether hydrogens are equivalent or not. I think there was another question here also. Just say 0.7 to 1.3. Yes, I put 1.6 because it isn't too far from oxygen. Okay, that is why I put 1.6. But if you have 1.3, that will be fine also. Okay. Now let us do D. Let me go ahead and erase this. Hopefully, by doing this, you get to familiarize yourself with those chemical shift data, with some of the range where you expect them to be. Okay, so let us do this. D. We have 3,3-dichloropentane. 3,3-dichloropentane. Okay, that is 3,3-dichloropentane. Okay, now let me ask you this. How many different types of hydrogen do you have in this molecule? How many? 2. Okay, great. Okay, great. Okay, so let us look at the 2. We say this is one set. This, let me change the color of my pen. We say this here, this set will be the same equivalent to this, because this is a symmetrical molecule, and also this set and this set are equivalent. So therefore, I would expect to get only 2 chemical shift signals for this compound. Okay, so now let us go ahead and give the complete set of data. Okay, let us start with this. What will be the chemical shift of this? Any idea? 1.3, okay. Let's go with that, 1.3. What will be the multiplicity? Multiplicity for this here. Triplet, because it is only seeing 2 triplet. So that is a triplet. Okay. How many hydrogens? How many hydrogens? Don't forget this and this are in the same molecule, they are equivalent. 6. There are 6 equivalent hydrogen giving the same chemical shift. Okay, good. How about this one here? The chemical shift for this? Chemical shift for this? Not too far from chlorine. Okay. Okay, 1 point. Okay, you say 1.6? Okay, I'll take that. Okay. What would be the multiplicity? Okay, somebody say 1.8. Okay, I'll take that too, 1.8. That is still within the range. Okay, about the multiplicity? Quartet? How many hydrogens? Take a look at the complete molecule, 4. Because you have these 2 here and these 2 here. Okay, both of them are giving the same set of data. So this is 1.8. Okay, good. And therefore, this is the NMR data for this molecule. Okay, which is this one here. Okay? Now let us now do this one here. Let us do this. Okay, at this point I am going to erase this so I give myself some room. Okay. 1,2-dimethyl cyclobutene. Okay, what does that look like? 1,2-dimethyl cyclobutene. 1,2-dimethyl cyclobutene. You also notice there, we are also testing your knowledge of nomenclature. Okay. So, what is the question I want to ask you? How many different types of hydrogen do you have here? Somebody said 3. Okay. How many people said 3? Okay, let us see. Do we have 3? Do we have 3? Okay, somebody said 2. 2 is correct. This is one set, this methyl, and this methyl will be one set because this molecule is symmetrical. There is no hydrogen here. Okay? And then you have this here, these 2 hydrogen here, and these 2 hydrogen here will be equivalent. So that is only 2 sets of hydrogen. Okay? So, what will be the chemical, the PNMR data for this? The complete set of PNMR data for this. What will it be? Let us start with the methyl. What is the chemical shift of methyl that is attached to a double bond? Take a look at your chart. It should be somewhere around 2.5, 2.2. Is that what you said? Take a look at your chart. 2.2, okay, I'll take 2.2. Okay, in this case, what would be the multiplicity? Notice there is no hydrogen here. Singlet. Excellent. Okay. And then, how many hydrogens? 6. 6 hydrogen. Because you have to take a look at the complete molecule. Now we come to here. Okay, this is a CH2 that is attached to a carbon-carbon double bond. What will be the chemical shift? Take a look at your chart. We should be close to 2.5. No, let's say 2.5. Okay. Okay, what will be the multiplicity? There's no hydrogen here. Multiplicity? Singlet. Exactly. How many hydrogen? 4. 4 hydrogen. Okay, very good. So you guys are getting very good at this. So therefore, all we've done here, this is the complete set of PNMR data proton NMR data for this molecule, which is this one here. Okay? Okay, we have two sets of hydrogen, and therefore we have only two chemical shift signals, this and this. Okay, very good. What do somebody say? Okay, go ahead and ask your question. Why 2.2? If you take a look, which one are you talking of? Why 2.2? Take a look at your chart. There is a range there. Well, all we are doing is simply using numbers within that range. Okay, so let us go to the next question. Okay. That is, no, you're looking at a CH2 that is attached to a carbon-carbon double bond. Okay? Okay, now let us look at this. Praveen, go ahead and read this question for us.
Can you hear me? It says, propose a structure consistent with each of the following set of NMR data and indicate which protons, when appropriate in the molecule, are responsible for the signals.
Okay, thank you. Very good. Now, what is wants you to do here, propose a structure consistent with each of the following set of NMR data and indicate which protons in the molecule are responsible for the signals. If you notice here, this question here is the reverse of the question we just did. In the question we did, we told you to give us the PNMR data. We gave you the structure. In this case here, they have given us the PNMR data. Now they say, give us the structure. Okay? Here, we have a molecular formula of C4H7 bromine and oxygen. If you look at this here, whenever you are given a formula like this, I will advise you determine the index of hydrogen deficiency. Index of hydrogen deficiency. I hope you guys have not forgotten that. Okay, now, if you look at the index of hydrogen deficiency for this here, it is actually, it will be 1. It will be 1. IHD, index of hydrogen deficiency, will be 1. Okay. Okay, now, I will take a look at this, very close look at this. I say, somebody asked me a question. No, wait, I forgot to include the halogen. Okay. Okay, so now we have C4H7, bromine, and oxygen. I will look at the the most obvious information. I will see there 2.11 singlet, 3 hydrogen. Okay, I will take an educated guess, knowing that this molecule has 1 index of hydrogen deficiency. I will say 2.11 singlet, 3 hydrogen. The chances are this will be this here. Okay, and that will be my index of hydrogen deficiency right here. Okay, at this point, I only have 4 carbons to go. You only have 4 carbons to go. So now I need 2 more carbons, right? And those carbons, each one of them is attached to 2 hydrogen. So what is this is telling me? I have 2 CH2s. So this is a very small molecule. I don't think you can go go too far out on this one here. You only have 4 carbon atoms, 7 hydrogen, bromine. Now, to complete this molecule now, because we have accounted for everything in this molecule, All that is missing is bromine. Okay, so you have to take the educated guess, in this case, starting with, you say, okay, this here, the chances are this is a methyl attached to carbonyl 2.11. Now, let us now see whether we could assign chemical shift to this here. I would say this here, because it is next to bromine, electron withdrawing, so therefore that would be the 4.4 parts per million, and this one here will be my 3.52 parts per million, and of course this is 2.11 parts per million. This structure is consistent with the data that they have given us. That is what you want to do. Whatever the assignment you make for your molecule or for your structure must be consistent with the data that you are given. The formula is right, and the chemical shift data is also consistent. Yeah, go ahead and ask your question.
So the methyl that's attached to the halogen is going to have the higher ppm?
Yes, in this case, yes, because the halogen is electron withdrawing, just like oxygen is electron withdrawing, so therefore you will expect that to have an impact on the chemical shift of this hydrogen here, greater than it will have an impact on the chemical shift of this hydrogen. Okay? Okay, now let us do the B part. Let us do the B part. We have 8 more minutes to go. Okay, B part. This one here, you have a formula for this is C5H10 and 1 oxygen. Okay. Once again, the index of hydrogen deficiency for this IHD equals to 1. So, once again, I will take another educated guess. Look at this here. 2.1 singlet to the hydrogen. Say it is possible that I have this. One index of hydrogen deficiency, and that will take care of that. Notice here, we only have 5 carbon atoms so far. Now, what other information is obvious to us? We have septet, we have doublet. What does that tell you? Septet and doublet. Isopropyl, excellent. Isopropyl. So therefore, if you have isopropyl here, that will take care of all of the remaining carbon and hydrogen that we need. So in this case, simply take a look at the data that you are given and look for the most obvious information, and then begin to put the pieces together. That's what you do in this kind of problems. Okay, let us do the assignment. Okay, this one here, this is your 2.10, which is this here, which is a singlet. And this here, this is your 2.43. This here, which is a doublet. I'm sorry, which is a septet, because it is this hydrogen here is seeing 6 equivalent hydrogen, 6 hydrogens. So that is why this is a septet. 6 plus 1 is 7. Okay, and then this methyl here and this methyl here, that is what you have here, 0.95, 0.95, and that is a doublet, 6 hydrogen. Okay, do you have any question on this? Okay, we are moving right along. Let us now do, okay, we only have 2 more problems to go, then we call it a day. Okay, this one here. This one here. Okay, now, what do we have here? Let me see. May I read? Can you go ahead and read this question for us?
Propose possible solutions for each of compound A, B, and C below. For compound B, the signal at 1.6 ppm should be considered a multiplex. For compound C, the signal at 7.2 ppm should be considered a singlet. Also, for each structure, you must assign the chemical shift to different protons in the molecule.
Okay, thank you. Very good. Okay, now, so what have they done here? We actually have 3 sets of compounds here, and that is why I have B and C here, 13B and C. Okay, the molecular formula they've given us for this compound is C5H10 and 1 oxygen. Now, folks, you remember what I told you? Whenever you have a spectrum given to you, what you want to do is to convert the data from the spectrum to a tabular form. Okay, so let us do that, because once you do that, it makes things, you see things a little clearer. Okay, let us do that. Let us convert the data to a tabular form. Okay, keep in mind that this peak here, that is this here, it's a triplet, okay? And this peak here, that is this here, and that is 1, 2, 3, 4, 5, 6. That is a sextet. Sextet, because it's 6. This here is a singlet. And this here is this here, triplet. Okay, so let us go ahead and assign and write the tabular form of this data. Okay, the peak, what is the first peak? Can you give me the chemical shift of the first peak? Somebody? 1. Very good. 1.0. Okay, and that is what? That is a triplet. That's what they gave us. And they told us that is 3 hydrogen. That is this 3 hydrogen here. Okay? What is the next one? This one here. What is the chemical shift? Okay, 1.7. Okay, good. The multiplicity. Okay, 1.7, 1.8. Multiplicity. Sextet. Okay. Okay, multiplet. Okay, very good. Okay, sextet. Okay, because it is 6. And then the number of hydrogen is 2. Okay, the next one. What is the next one? What is the next one? Chemical shift? 2.1. Okay, good. 2.1. And that is a singlet. And that is 3 hydrogen right here. Okay. And the last one, this one here. What is the chemical shift? 2.4. Okay, good. And that is a triplet. And that is 2 hydrogen. Okay. So now we have the data that we want. Let me see here. Okay, so what do we think the structure will be? I will start with the most obvious information once again. I will start with this one here. 3 hydrogen, singlet 2.1, which is this here, right here. Okay, I will assume, because you have an IHD here equals to 1, I am going to assume that that is a methyl that is attached to a carbonyl. Okay, so that will be my 2.1. Okay, now keep in mind this molecule only has 5 carbons, so you only have 3 more carbons to go. Now what do we have here? We have a triplet. We have a triplet, 3 hydrogen. So what does that tell me? It means that we have a methyl group. somewhere here, I will write that here, attached to a CH2. That is why it is a triplet. Okay, very good. Okay, so can you please explain how you got that structure for 2.1 again, please? Okay, if you look at your chart, because what we have here, we have 3 hydrogen at 2.1. That is what they gave us. If you look at your chart, what could be 2.1 and 3 hydrogen could either be a methyl that is attached to a carbonyl or a methyl that is attached to a carbon-carbon double bond. And since we have oxygen in this molecule, I am simply taking an educated guess at this point that this is a carbon-oxygen double bond that is attached to a methyl. So that is why I assigned 2.1, this 2.1 to this one here. Okay. So now we have 1.0 triplet, 3 hydrogen. So I would say we have this relationship here. Okay. So now I have taken care of this in a way. I have taken care of this, and then I have also taken care of this. Now I need to take care of only this here and this here. And what do I have here? This one said 2 hydrogen triplet. What that tells me is that this 2 hydrogen here is only attached to another 2 set of hydrogen. Okay, so I will say if that is the case, I have CH2, okay, next to a carbonyl. That is why it is 2.4. Now, it could be attached to this because we only have 5 carbon in this molecule. If I accounted for all of the 5 carbon. Now, how then do we get the sextet? If you look at this one here, look at this hydrogen here. How many hydrogens are this hydrogen seeing? How many are they seeing? This hydrogen? 5. And that is now why you got 5 plus 1 equals to 6. And that's how you got the sextet. Okay? So this is a case of simply putting the pieces together. Okay? You put the pieces together to make a complete structure. Okay, in this case, okay, somebody say that again. This CH2 here, this set of hydrogen here, it is looking at 3 hydrogen here and 2 hydrogen here. Okay, and so if we apply the n plus 1 rule, therefore the multiplicity for this hydrogen will be a sextet, or sometimes it could be called a multiplet. Okay? Okay, so that is how we got this structure here. So let us now go to the next one. Okay. Okay, keep in mind the same set of questions that we just did. This is just B part. This is the B part. Okay, so the formula here is C7, H7, and bromine. C7, H7, and bromine. Okay. If you look at this molecule, this is a very simple spectrum. A very simple spectrum. Whenever you see, if you look at this region here, remember what I told you, what do you find in this region? Can anybody tell me? What kind of fragment do you expect in this region? If you look at your chart, benzene type molecule, what they call aromatic molecule, right? Okay, very good. So, whenever you see this kind of multiplicity here, you have this here, you have this here, it's almost symmetric. 2 hydrogen, 2 hydrogen. What does that tell you? That tells us that the benzene is a disubstituted benzene because you have 2 hydrogens left. Not only is it telling us that it is disubstituted, it is also telling us the substitution pattern is right here. In other words, whenever you see in the benzene region you have two peaks like this, in which one is 2 hydrogen, the other is 2 hydrogen, and they seem to be symmetrical. What that is telling you, you have the substitution or the attachment to the benzene ring in a 1-4 relationship to each other. 1, 2, 3, 4. Okay, this is what we call para substitution. Okay, so now you have hydrogen here, hydrogen here, hydrogen here, hydrogen here. Okay, that is why you have 2 hydrogen, 2 hydrogen, because this hydrogen and this hydrogen are equivalent. This hydrogen and this hydrogen are equivalent. Now the next, I know somebody is asking a question. Just a minute. How do I know that that is para substitution? Anytime you see this pattern in the aromatic region, in other words, you see a pattern like this, which is symmetrical. Anytime you see that pattern in the aromatic region, that tells you that the benzene is disubstituted and that the substitution is this kind of substitution right here. So that is what that is telling you. Okay, you need to know that. Okay? Okay. At this point, our formula is C7, 7 hydrogen and bromine. Okay, so far we have 6 carbon here. So that tells us we also have 3 hydrogen here. So what that is telling you, you must have a CH3 here. And since you also have bromine here, you must have bromine here. Okay, do you follow that? In other words, the structure for this now, this is the structure. Okay, and that takes care of the this problem, because the formula is C7H7Br, and that takes care of that. You have 3 sets of hydrogen. This one set of hydrogen, and the other set of hydrogen will be, okay, this is one set of hydrogen, this is the second set of hydrogen, and this is the third set of hydrogen, because this and this are equivalent. This and this are equivalent. So you have 3 sets of hydrogen, 1, 2, and 3. What happened to making the table structure first? Do we? Oh, yeah, you could do that. Yes, you could do that. I told you to make the table structure first, just to help you out. The reason, because we are getting to the end, that is why I just did not do that. Yes, you could go ahead and make the tabular form of the data before you do this. It isn't that you don't have to do that. Okay, you don't necessarily have to do that if you know what you are doing. Oh, the metric group could be, doesn't matter whether it's at the top or at the bottom, it's the same molecule. Okay, somebody asked why not the metric group here and the bromine here. It doesn't really matter. Okay. Okay, so let us go to the last set on this. Okay. Now, this is another molecule here. Let me ask you, think of this as a singlet. That's what they told you here. The signal at for compound C, the signal should be considered a singlet. That's what they told you. Okay? So consider this a singlet. Okay, now let us look at what we have here. This peak here is this one here. And this one here is this one here. All they've done is simply just to expand. This is actually a triplet right here. This is also a triplet. Okay? So that's what they've given you. In other words, this peak at 3.1 and this peak at 3.7, they are triplet. Okay, so let us write out the tabular form so I do not break my own rule. Okay, so we have a peak at 3.1. That's a triplet. We say it is 2 hydrogen. That's what they gave us, 2 hydrogen. And then you have a peak at 3.6. Okay, that is also a triplet. And that is also 2 hydrogen. And then you have this peak here in the aromatic region. We say that is 7. What do you want to call that? 7.2. We say that is a singlet, and that is 5 hydrogen. Can anybody give us the structure of this molecule here? Given the fact that the formula is C8, H9, and bromine. Can anybody guide us to the structure of this molecule? What is this? Does this tell you? Ring. Okay, great. Okay, very good. Once you know that, then your problem is solved. Okay, you say you have an aromatic ring. Okay, if we say we have an aromatic ring, okay, we have 5 hydrogen. So what is that telling you? Okay, somebody gave us the answer already. Very good, excellent. Because that means you only have 1 substitution in this molecule, in this ring system, CH2. Very good, you guys already got the answer for me. Okay, and that is that. So let us assign the peaks. All of these hydrogen here, we will consider them as singlet, as equivalent, and that is the 7.3. And this one here, this will be the 3.6, and this will be the 3.1. Okay. Okay, so let us do one more problem and then we call it a day. I think we spent over 1 hour already. The reason why I generally want us to leave in 1 hour is because if we stay too long, the file for the video will be so large, you guys may not be able to open it. So let us do one more problem and then we call it a day. Let's see here. I do want us to do this problem here. Okay. Now, problem number 15. Let's see. Oluche, can you go ahead and read this question first? Okay, she may not be.
NMR data with pH splitting for compounds A and B. Provide structure for A and B.
Okay, thank you. Very good. Okay, so what they are asking us to do here, below are the carbon-13 NMR data with carbon-hydrogen splitting for compounds A and B. And they say provide structures for A and B. Now, before we do this, let me give you a little bit of information. With respect to carbon-13 NMR, the rules are similar to the proton NMR. In carbon-13 NMR, if you have this, say we have this molecule here. If I ask you, how many different types of carbon do you have in this molecule? How many different types of carbon do you have in this molecule? How many? Anybody? How many let me see. Okay, 1. Okay, great. That is correct. That is correct because this carbon and this carbon will be equivalent. Okay? The same set of guidelines that you use for the proton, you use for the carbon. Okay, supposing I give you this here. How many different types of carbon do you have in this molecule? This one here. 2, exactly. The same type of guideline. Now, In the case of carbon-13 NMR, if you notice in proton NMR, the chemical shift data for proton goes from, you have TMS, you go from 0 to 12 parts per million in proton NMR. On the other hand, in carbon-13 NMR, the chemical shift data goes from, if we say this is TMS, which is 0, it extends to 200 parts per million. Okay? That is the only difference. Now, I've been giving you that. Also, in the carbon-13 NMR, when it comes to splitting, or spin-spin coupling, or what we call multiplicity, in carbon-13 NMR, if you look at this here, in the multiplicity for this, to determine the multiplicity, you look at the number of hydrogen that is attached to the carbon atom. Okay? Look at the number of hydrogen that is attached to the carbon atom. So how many hydrogens are attached to this carbon? Can anybody tell us? How many hydrogen are attached to this carbon? Okay, let's see. Okay, 3. Okay, great. Therefore, in the case of carbon-13 NMR, the N+1 rule, so this carbon, therefore, will be a quartet. Okay? So what will be the multiplicity of this carbon? If you go by that rule. What will be the multiplicity of this carbon? A triplet, exactly. That is how it goes. Now, if you look at this molecule here, how many signals, how many carbon-13 NMR signals do you expect to get? 2. So therefore, the chemical shift, the carbon-13 NMR data for this will look like this. If you look at, if you go to, I believe the data is on page, let me look at this here. Go to page 465. You see the chemical shift data for the different types of carbon on page 465. For example, this is what it looks like. Somewhere between about 180, from 180 to 200. This is where you expect to find the carbon that is attached to a oxygen atom. In other words, carbon-oxygen double bond. That is where you expect them. You will see that on page 465. Now, if you are the aromatic region, the benzene region, you have this here, the carbon of benzene, you have them somewhere between 120 and 140. So what I'm simply doing here, I am giving you what you have on that page 465. Now, the other type of carbon, depending on whether they are attached to electron withdrawing group or not, you find them somewhere between 0 to about 120. So anyway, so that is just to give you a background as to the chemical shift information on carbon-13. Okay, I haven't said that. Let me take this out. So therefore, if somebody asks me to give the carbon-13 NMR data for this, this is what it will look like. It will look like 20 parts per million for this carbon here, And then the multiplicity will be a quartet. And then the number of hydrogen will be what? How many hydrogen? I'm sorry, how many carbons? It will be 2 carbons, right? Okay, 2. This here will be maybe about 25 parts per million. This is based on the chart on page 465, and that would be a triplet. And only 1 carbon. Okay, so that would be the carbon-13 data for this one here. Okay, now let us now solve this problem. We solve this and then we call it a day. I think we've spent over 1 hour already. Now, provide the, yes, somebody asked a question. Go ahead. Oh, I will post this. I will post this. I will try to post this somewhere between by 11 o'clock tomorrow. I will post it. Okay. Now the question is, below are the carbon-13 NMR data. This is what they call carbon-hydrogen splitting. Okay. In other words, the carbon and hydrogen are splitting each other. The reason why we say that here, it is also possible to run carbon-13 in a mode in which hydrogen and carbon are not splitting. But at this point, do not worry about that one. Okay? So let us now give the structure for this. Provide structures for A and B. Can anybody give us the structure for this here? This is the formula. Can anybody give us the structure for this? Okay, this is the formula for, exactly. Excellent. You guys got it, okay? It is butane, exactly. It is butane. You see how simple that is? Because you only have two types of carbon, which is this here. This is one type. This is the second type. Okay? And then you have quartet, meaning that you have a methyl group, and then you have a triplet, meaning that you have a CH2 group. Excellent. That's simple. Okay, now let us do this one here. C5, the formula here is C5H8 and oxygen. Keep in mind we now have a chemical shift at 170. Remember what I told you, that region. If you look at your chart, okay, what do you think this will be? You only have 3 types of carbon here. You only have 3 types of carbon, and the formula is C5H8, 1 oxygen. What will it be? Methyl ketone. Okay, let us see. Do we have that? Because this here, this is your carbonyl, 170. That's carbonyl exactly. Okay, you only have 3 different carbons here. This is 1, this is 2, and then you have a triplet. Would that be right? Okay. Would that be right though? Okay. Now, methyl ketone, I don't think that would be right because look at this here, index of hydrogen deficiency. Look at the index of hydrogen deficiency. What is the index of hydrogen deficiency here? 2. IHD is 2. Exactly. Now, we got to be a little bit more crafty on this. What do you think this will be? We have 3 types of carbon, 5 carbons. Okay, we know we have a carbonyl, right? Okay, we have 4 more carbon to go, and therefore we must be dealing with a symmetrical molecule here. Okay, 1, 2, this is one type of carbon. This one is another type of carbon. And this is the 3rd type of carbon. Okay? You look at what we have here. Once again, it's a case of putting the pieces together. This here, this is the chemical shift at 170. This carbon here, because it is next to carbonyl, that would be the one that give you the chemical shift at 28. I'm sorry, chemical shift at 40. Because this triplet also. And finally, this carbon here, that will be the one that gives you the chemical shift at 28. Okay? Okay, and so you have 3 sets of carbon in this molecule. Keep in mind that this carbon and this carbon are equivalent. This carbon and this carbon are equivalent, and that is why you have only 3 sets of carbon in this molecule. And the molecular formula fits this formula here, C5, H8, and 1 oxygen. So folks, we have come to the end of today's session. I will stay behind for another 5 minutes. I will turn the mic off for those of you who may want to ask me additional questions, but the session will be officially over. Now, before I turn the mic off, do you have any questions? Okay. Okay, so let me turn the mic off and then just stay online and ask your questions. So, for those of you who are leaving us, I will see you tomorrow. Enjoy the rest of your evening. Okay, I'm going to turn the mic off now, or the recorder off.